In this problem, we're putting a crude lower limit on the period of rotation of the white dwarf left over after our sun dies. So we're making a variety of sort of reckless simplifying assumptions to make it so this is accessible for introductory physics. Basically, I'm going to treat this like a rotating rigid sphere that just suddenly collapses into a smaller amount of space. And we're starting at a radius equal to the radius of our sun. It says 696,000 kilometers, and ending at a radius equal to a typical radius for a white dwarf. And I put 7,000 kilometers on that. So you should notice that a white dwarf has a radius that's comparable to the radius of Earth. And this is true in general, that a white dwarf is like the mass of a star crammed into the size of a terrestrial planet. So it's incredibly dense stuff. So before we get into the conservation of angular momentum, I wanted to point out that we're given period here, and we're used to talking about angular velocity, omega. And I wanted to talk about the relationship between those two things. So omega would be measured in radians per second. If I were to multiply by one rotation for every 2 pi radians, that would give me rotations per second. In other words, omega over 2 pi gives me rotations per second. But period is seconds per rotation. So we just sort of informally figured out that period is going to be the reciprocal of this thing. It's 2 pi over omega. And that'll be handy for this calculation. Let's get into the conservation of angular momentum part. So L initial is equal to L final. And L initial is the initial moment of inertia times the initial angular velocity. Likewise for the final quantities. And the initial moment of inertia is going to be 2/5 m. And again, we're assuming m is not changing. Not true for real stars, but it's a good first approximation. M times the radius of the sun squared. Omega initial. In the final state, same mass, but now it's the radius of a white dwarf. And the 2/5 cancel out, and the m's cancel out. And I end up with radius of the sun squared omega initial is equal to the radius of the white dwarf squared omega final. And then I want to rephrase this in terms of period. So my initial angular velocity, I could solve for omega here and write it as 2 pi over t. Same thing on the right-hand side. And that's that final period that I'm trying to solve for. The 2 pi's cancel. I'm going to move the final period over to the left-hand side, everything else to the right. All right, so we've basically solved the problem symbolically, and it's a matter of getting some numbers in here. But there's one thing left to do in terms of preparation. I've got to take the period of the sun in days and do some unit analysis on this. Sure, we could come out with an answer for the white dwarf in days, but it's not going to turn out to be a very appropriate unit. So I'm going to switch to seconds. And I've got 24 hours in a day. And I've got 3,600 seconds in an hour. And when I do that, I come out with 2.117 times 10 to the 6th seconds for the period of the sun. All right, let's plug in and find the period for our white dwarf star. So it's okay to work in non-standard units here. I'm putting in kilometers because in this fraction, the units are going to cancel out and it comes out to be unitless regardless. Another way to say it is if you applied the same conversion factor on the top and bottom of a fraction, the conversion factors cancel, so it just doesn't matter. All right, and crunching my numbers, I get 214 seconds, or roughly speaking, 3.5 minutes.